have this molecule there. That's the bromine sitting on this carbon, this very long chain carbon. But that's the halide I provided to you. But along with that, I have two reagents shown in the reaction. One is a dioxide, and the other is an ethanol. If you remember that, that is a conjugate base forms of this. But this is two different things. So which one is going to go for the reaction in what way? That is something that you need to figure out. And right now, we're dealing with just the two reactions, SN1 reaction and SN2 reaction. So let me simply ask you, do you have to approach this question considering SN1 as your mechanism or SN2 as your mechanism? That will change the answer depending on what you choose. See, this is the kind of dilemma you're getting to. I'm not telling you, give me the SN1 product, give me the SN2 product. Later on, it's going to be the elimination reaction coming down there too. So I'm not telling you, give me the substitution product, give me the elimination product. I'm going to ask you, what will be the product? So you need to figure those things out. But let me think about one thing. You know that alkyl halide react with a nuclear bomb. We can imagine these things attacking that carbon, kicking the bromines out. That is what we can expect. And then once that happens, we get this, right? That is not going to happen, right? That is not going to happen. Why that doesn't happen? Not because of this. This is really good for the SN2 reaction because this is a primary alkyl, which is good for that. It's less stably hindered. There's a good leading group there, so that's good for the SN2 reaction. But this one, I'm telling you, it is not a good new compound. One thing that SN2 chemistry requires, good new compound. And this is a really bad new compound. So that's the reason why it doesn't happen. Then will it go for the SN1 reactions? So bromine is going to pop out. You're going to get the primary carbocation. And the primary carbocation captured by this stronger molecule there. That goes to the SN1 reaction and they make the product. What do you think? Is it reasonable? Well, at least we can see that there's a possibility there. Right? I'm not there that this is not happening. I mean, but why I'm crossing out is that there's a better way. And first of all, the reason why I think this is not going to happen well, that's a primary element. If you remember that carbocation stability is really critical thing for SN1 reactions, and then that makes a primary carbocation, which is the bottom of the list of the stability. Tertiary carbocation is way more stable than secondary. Secondary is a much better than the primary. If it's a tertiary, then I may think that SN1 primary will go, but this is a primary, that's why I think this is probably not a chance. I mean, unless you have something much stronger there. That is a conjugate base form of this molecule, that's a methoxide. That is a strong compound. Compared to this one, that one, if you drink it with a mildly diluted one, you may feel better. If you drink that one, you die. I guarantee. No one will survive by drinking this. So just having a one hydrogen away changes things completely. And that's how subtle the chemistry is. I mean, we know that this is really strong base that is not. So I can tell you that's the reason. That is a very strong base and very strong nucleophile. Really strong nucleophile. And then it seems statically not demanding alkyl halide there. So that's a primary alkyl halide, which is a really good substrate for the SN2 reactions. So it basically checks all the boxes for the SN2 reaction. For making SN2 reaction, you have a strong nucleophile, check. You have to have a less hindered alkyl halide with a primary alkyl halide. So this can happen very easily. This makes an attack, kick these bromines out, we get to form this. If you think about it, even SN1 chemistry make the same products in this molecule. But I'm telling you, how this forms is something that you also need to understand, not only just product. You may luckily guess the right product by going the wrong way, but eventually that will be the trouble. So I hope you understand how I kind of navigate the problems out, right? If there's a multiple pathways possible, then you need to figure out which way makes sense more to you. One other things I also made a point out is, if you somehow compare SN1 and SN2 together, let's say, primary alkyl halide, let's say, I know that's bad, I cross it out, but the thing is, maybe I shouldn't cross it out. Even though there's a 0.01% there, I mean, what's the possibility of the US soccer team winning the World Cup? How much chance do you give? 10%? 5%? Not 100%, right? Even if the team of Brazil doesn't get 100% chance either. So, but even though 0.01%, people still can expect that may be happening in some day, maybe a miracle game. However, it's not really realistic. This is a chance there. I shouldn't cross it out. Zero chance is not what I'm talking about. Maybe it gets a little chance there. This one, if it happening, SN1 competing with an SN2, right? Which one would win? So if you're going to think about that, SN1 reaction requires formation of the carbocation, which is an energy-driven, very slow process. This is a turbo. That's the head. I know. Unfortunately, the fable have a different ending. But if you got the small, slow guy and the fast guy starting the, for the race, which one gets to the finish line first is a fast guy. SN2 is a way more faster. So even though S1 has some chance, maybe 0.10% chance, let's say it has too much chance I give it, but even though I give it like a 10% chance it goes this way and make the same product, that is happening already. Molecule is not waiting for this happening. It gets done job fast enough, so you get things in an SN2 reaction. If the fast reaction compete a slow reaction, you got to go real fast. Okay? So let's talk about this one then. This one's a pretty simple one because you see the one alkyl halide, and then you got the one lead. It's kind of about simple as the other. But let's say this is the leukobar, right? You have a very big leukobar like this. SN2 reaction is something you shouldn't consider, right? It's only SN1. And then thankfully, what we have the tertiary alkyl halide is halogen chlorine sitting on the 1, 2, 3 carbon substituted carbon. That's a tertiary carbon. So if the carbon goes away, I mean, let's say if these attack this carbon directly by an SN2 manner, then we kick this chlorines out, we get that form, maybe we get this. And then that also you should expect the inversion of stereochemistry. If the chlorine was sitting on the top, if you attack to the bottom, it's going to move the chlorine to the top side, and then you could subject to the bottom side. So that's basically I drew it out by the SN2 reactions. This is not going to happen because that's too much steric hindrance there. And also, this is a bad leukobar. That's the things that we're talking about. Things are not happening with an SN2 reactions. It's a too sterically hindered carbon, right? The bad leukobar. So what we should expect instead of SN2 reactions is chlorine goes out as a chloride. You're going to form the tertiary carbocation. And then that tertiary carbocation, once you see any carbocation, I've been asking you, this question should pop in your mind. What it is? Will it be arranged? So, will it be arranged? That's a tertiary carbocation. By making this hydrogen group, it's going to be primary. By making that hydrogen group, that's going to be secondary. Hydrogen group there is secondary. So all the choices they're bad. So they're not going to move. They're already in a good place. So they're not going to move. So I'm telling you, these things are not going to go and stupidly move in the secondary carbocation and captured by these things. Not going to happen. These things is going to be just captured by the nucleus and the sorghum molecule there, and then go to the products. And then stereochemistry is going to be lost, right? Because it becomes a flat carbocation and a captured from the top and bottom 50-50 chance. So you don't have to show any stereochemistry for these products. There's a so many different way I can make the question harder, believe me. So that's why chapter 6 is really going to be eye-opening chapter for you, or the chapter requires a lot of aspects. We're not finished yet, but it's already kind of difficult. Let's say this one. This one's a pretty simple because you got that. That is sulfur negatively charged, right? And the sodium that there's a cation. So thiolate, this negatively charged sulfur, is a nucleophile. That is a pretty strong nucleophile, right? That is a pretty strong nucleophile. And what we see here, and even though you have a pretty strong nucleophile, if you have a tertiary alkyl halide, one thing that I've been telling you, steric hindrance is a really, really big thing for the SN2. Primary alkyl halide is good for the SN2 reactions. Secondary, yeah, it's okay. Tertiary, really bad. I mean, I never seen tertiary alkyl halide going for the SN2 reaction yet. I mean, I didn't all the SN2 reaction, so I wouldn't know maybe for the 100%, but I haven't seen any of the tertiary alkyl halide going for the SN2 reaction. So if you have a tertiary alkyl halide there, you may think that it's a strong nucleophile making SN2 to go, but that side is not taking it. But thankfully, this one is a 1,2 carbon substitute. That's a secondary alkyl halide. So, and this SN2 reaction can go. That sulfur is a nucleophile, not the carbon, right? Not the sodium. This thiolate, negatively charged sulfur, that's the center of the nucleophile. Makes an attack, kick the bromines out. But you really have to be careful when using a starting material, stereochemistry is defined, right? You didn't see this regular line. You saw it with a red to dash line, right? That means this is a stereochemically defined carbon. So when you have a reaction done, this sulfur is going to make attack to the backside and kicking these things out. So that is going to attach in the opposite side of the living rooms, right? That is something that I would expect in SN2 to be a stereochemical inversion. You gotta show it. It doesn't go through this way. I've been already telling you, SN2 reactions are way more faster than SN1. If there's a chance it goes through SN2, why the molecule should wait for the slow reaction, right? Things are already being consumed. But bromine comes off, just explaining, bromine comes off, making a carbocation, that's kind of path of SN1. And then this thing captures, and you make it a similar product without the stereochemistry. So if you answer this way for that mechanism, my mind is thinking that, oh, you chose SN1, not SN2. So your product show me what sort of process you imagine. But drawing out will be always better because we can see things. So that's not going to happen. And then rearrangement, of course, not of an issue because these things are possibility if you get a big nucleophile. That's a strong nucleophile. Things are not waiting for that happens. So now that reactions, you have a alkyl halide, that's the secondary alkyl halide, and then you got the methanol. Methanol is a neutral alcohol. I guess you can imagine that that's a bad nucleophile. So I don't think this is going to make an attack directly and make an SN2 reactions. That is not going to happen because it's bad nucleophile. So whenever you see a question, you really have to choose, is it going to be SN1, it's going to be SN2. Only way you can figure out by looking at what sort of alkyl halide you got, what sort of reagents you have. Strong nucleophile, bad nucleophile, stably hindered, not stably hindered. Those things are something that you got to consider to figure out, should I go for the SN1, should I go for the SN2, right? This is a bad nucleophile. No matter what you throw at it, they don't contain it. So these things are not going to happen. So only thing that makes it happen is wait until you got the bromine goes out as a bromide, you get the carbocation forms. Once you get the carbocation forms, then what did I ask you to think about? Yeah, you got to think about rearrangement every single time. I mean, once you figure that out, you might be happy, oh, finally I got it. You jump for the conclusions using it. You may regret that sometimes you have to figure out rearrangement possibility before you do that. I know there's a hydrogen here. This hydrogen moving out make a primary carbon cation. That's bad. So that's not going to happen. But these carbon having a methyl group, they don't have a hydrogen done. If they have hydrogen, it moves out, make a tertiary carbon cation, but they don't. However, we know that the methyl shift can also happen. Methyl groups move out. I mean, that's going to slow, but it's going to make a tertiary carbon cation. So we got the possibility of the forming more stable carbon cation by making methyl groups. And obviously, these things are kind of not that fast. So this carbon cation still exists. It can capture the solvents that you get this product as in one product from the original carbon cation. If the method is the solvent capture the rearranged carbon cation, you are forming this. Obviously, we have to choose which one is going to be major. The ratio of major minor is going to get smaller. The gap is closing, but I still believe that's going to be the major product because of these more stable products. I know carbons are shifting slow, but eventually it's going to perform better, and then that's going to work for the reaction. But it's not going to make the same SN2 reaction. That's not going to happen. SN2 is not going to happen because it is a very bad nucleophile.